Hello guys, welcome to Math 10, Week 10 of Math 120. This week we're going to spend all of our time talking about confidence intervals. Um, this week we're going to spend all of our time talking about confidence intervals. You can get a good idea for the material that we're going to cover in the book by reading section 5.2. So if you haven't yet, I really recommend pausing right now, open up the book, and take a look at section 5.2. It's okay if you don't understand every word that's there, but I know it'll help if you can think about it before we start doing it here. Okay, so now that we know about sampling distributions, in other words, now that we can say how likely or unlikely a particular sample result is, we can do the two big useful tools that we talk about in this class. I think really what we're going to do for the rest of the semester is the most important stuff that you're going to learn in this class. If you go out into the world and ever do any statistical analysis, almost certainly that's going to be in the form of either a confidence interval, which we're going to do today, or a hypothesis test, which we'll talk about next week. Both of these things are examples of statistical inference. That's a word we've kind of focused on a bunch over the course of the semester. Remember, statistical inference is the process of making mathematically supported conclusions about a population based on our sample statistics. We want to go beyond the data that we actually have and say something about the population that it came from. So, let's start with confidence intervals first. So, here's the idea. You guys remember, a statistic is a numerical summary of a sample. We've got sample data, we can summarize it in lots of different ways, and we've seen lots of different statistics in this class. They're important, of course, because the name of this class is statistics. We're really going to continue to focus on two statistics in particular for the rest of the semester. There are two big ones we're going to think about. First, if we're talking about categorical data, then the statistic we want to think about is a proportion, p hat. On the other hand, if we're thinking about quantitative data, then we want to talk about an average. In other words, x bar. In this video, we're going to do p hat, but we'll do both. Next time I'm going to do x bar. And for the rest of the semester, we'll kind of bounce back and forth between these two different types of statistics that we want to think about and analyze. Okay, let's think about an example. By the way, just as a reminder, I think there's kind of a lot on this page, but remember, you guys can pause. Might be a good idea to pause right now and just scan through everything I've got on the screen, just so that when I talk about it, you already kind of have an idea of what I'm saying. We've seen that statistics vary randomly because samples vary randomly. Every time we take a random sample, we're going to get something different, and that means the numerical summary we get, the statistic, is also going to be different. We'll get something different every time. Imagine, for example, that we're talking about the proportion of Denison students who are international students. Now, keep in mind, this is a categorical variable. That's why I'm asking you, that's why we're doing the proportion for this one. Population in question, all Denison students. The variable that we'd be wondering for this particular example is whether or not a particular student is an international student. Again, that's a categorical variable. It's not a number. We're not counting something or measuring something. And so the statistic that we think of for this variable is p hat, the sample proportion. Every time we take a different sample, we're going to get a different sample proportion because, of course, we will. We'll have different students in the sample. So there's going to be a different number of them that are international students. What we really want to do, though, is acknowledge, okay, samples are always going to vary. What smart things can we say about the population based on this? By the way, I don't know if you notice on the screen, I'm trying to highlight the text that I'm talking about as I talk about it. So here, I'm right here right now. We know that the samples are always going to be different. So in that case, what can we say about the population? Our sample proportion is never going to be dead on. At least we can't expect that it's going to be dead on. So we need to make some sort of estimate for what's going on with the population based on this sample result. And remember, just like statistics are numerical summaries of samples, parameters are numerical summaries of populations. We're trying to say something smart about these parameters based upon the statistics we're seeing. If we were in person right now, whenever I talk about statistics, I gesture downwards. Like statistics, they're the things that are on your laptop or on your notebook or the actual data that you've collected. Parameters live up here. They're kind of up in the clouds. We never really know what the parameters are because it's really hard for us to know what's going on with an entire population. We're trying to make an educated guess. And the big idea here is that since we know the probability distribution for these sample results, since we know how likely or unlikely particular sample results are, we can use that information to say something about the population. Because of that, these are backwards problems. All of these confidence interval problems that we're doing right now, they're backwards problems. They're going to be very, very similar to the backwards problems that you've done so far. So I hope once you get a little practice, they'll feel familiar in that sense, because they're actually just the same. Maybe to say that in one other way, I think I've said it out loud, but to repeat, confidence intervals are a way for us to estimate what's going on with the population. We know our sample result probably isn't going to be exactly right. There's got to be a little bit of wiggle room. Based on our sample result, where do we think the true population value is? That's what this technique is all about. I think maybe that's even the most important sentence of everything on this page. Confidence intervals let us estimate parameters based upon statistics. Here we're doing p hat and p. We'll do other examples too. Okay, let's take a look at some of the math behind this. I want to remind you guys, this would be a great time to pause and scan through everything that we've got here on these notes. There's a lot of information here. I'm going to talk about it right now. But I think that if you can read it first, it'll make a lot more sense when I say it out loud. You guys remember from our previous problems that when we're finding z-scores, here's the formula. It looks something like this. Z-scores are always observed minus expected over the standard deviation. Think about that. Think about what I just said. Z-scores are always observed minus expected divided by the standard deviation. If we're talking about categorical data, our observation is p hat, the sample proportion. The thing that we expect it to be is p, the population proportion. And we've seen that the standard deviation is this big, complicated square root stuff. This is in your text, by the way. If you take a look at the reading right here, you can see it's right in the middle of the screen. You can see the standard deviation there. That's maybe a prettier version of what that stuff looks like, do take a look at the textbook. So, oh, and another thing too to point out, this might seem a little confusing at first, but remember, when we're doing those backwards problems, we've always got two bounds. There's the lower bound and the upper bound, because we're talking about like the middle 95%, the middle 90%, the middle 99%, whatever. There's going to be a bound down below and a bound up above. Think about, let's imagine that my head is the normal distribution. And we're thinking about like the middle portion of it. That's the type of problems that these things are. Middle 95%, middle 99%, whatever. That's the stuff in here. We know we got a lower bound and an upper bound, and we got to get both of those things, right? So we need both the plus and the minus. If this seems unfamiliar, go back to week 9, pause the video right now, go to our lecture notes online, and read through the backwards example for proportions, p hat backwards example. You'll see this exact same thing going on there. Now, if you do a little bit of algebra, we can rearrange this formula a little bit and solve for p, the population proportion. You can try the algebra on your own. It's not too tricky, but you can also just trust me, and this is the same formula that's in the book. If you solve for the proportion, you'll get it's equal to p hat plus or minus z square root blah, 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 blah. This is just the backward z-score formula. This is the backward z-score formula. This is exactly what you guys did before. Again, we're going to do both the plus and the minus because we've got a lower bound and an upper bound. And just to make sure we feel okay about what all of these things are, p hat, of course, is the sample proportion. Z, those are the cutoffs for the middle whatever percent. Middle 99%, middle 95%, whatever you want to do. We want to think about the middle most likely values. That's what the confidence interval is all about. And n, of course, is our sample size. There is one little issue, though. The reason that we're doing this is because we don't know what the population parameter is. Think, we are trying to estimate p. We're trying to estimate p. So because of that, and I'm talking about this little problem right here. Don't be afraid to pause. Because of that, there's something in the formula that we don't know. Here, this stuff that I'm highlighting right now, we don't know what p is. We're trying to figure that out in the first place. So crap, what are we going to do? Well, we're going to do the next best thing and use p hat instead. We're going to do the next best thing. We don't know what p is. We'll use p hat instead. And as long as our sample size is large enough to satisfy the central limit theorem, that's going to be okay for us. So, altogether, here's what the formula looks like. Most important part right here is this stuff that I just highlighted. Maybe it'd be a good time to pause and take a look. Altogether, if we've got a sample proportion, p hat, from some random sample of size n, and as long as n is big enough for the central limit theorem, that means we need np to be at least 10 and n times 1 minus p to be at least 10. Then we can estimate the true population proportion. We're trying to say something smart about p. It's got to be somewhere between these two bounds. It's got to be somewhere between, typo, p hat minus z times the square root blah, 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 and less than p hat plus the square root of blah, 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 blah. P hat's in the middle of this thing, and we're looking at the wiggle room on either side. Where do we think the population proportion has to be? It's got to be somewhere in there. Maybe to make a picture of this stuff. It's hard for me to make a picture here, but I think I can still show you. If we think about p hat being in the middle of this stuff, p hat's our starting point, our guess for what the population parameter is, then our confidence interval has to go out a little ways from both of those things. So something like this. Can you imagine that I'm making a little picture of a confidence interval? P hat is our estimate. But we know there's got to be some wiggle room in this thing. We're not always going to get dead onto the right stuff. That's the interval. We think that the true population parameter lives somewhere in this range. That's what this technique is all about. Let me show you a specific example, and I think this will make sense. Actually computing these, doing the math for this stuff, is actually pretty easy to do, especially with a little bit of practice. Don't be intimidated by the formula. I think that if you do a few of these are some of the easiest problems that we do in this class. The actual math is easy. Let me show you. Here's an example. This example says, suppose that we take a random sample of 100 Denison students, and we find that 55 of them are female. Based upon this, let's estimate the proportion of all Denison students who are female with 95% confidence. Little heads up here. That word estimate, in statistics, estimate always means confidence interval. Estimate always means confidence interval. That's worth typing up. Note, estimate means confidence interval. In other words, we want to see what's a reasonable range of values for this population proportion to be of all Denison students. What proportion of them do we think are female based on the sample results? Now, before we get too far into this, we need to ask a question. Is n big enough? Is n big enough for the central limit theorem on this stuff? And remember, we've got two checks. We need n times p to be bigger than 10, and n times 1 minus p to be bigger than 10. A really easy way of checking that for these problems, i.e., need 10 in the category and 10 not in category. That's the success-failure criterion. Your book calls it the success-failure criterion. We need at least 10 successes and 10 failures. And I can see right away, yes, we definitely do. We've got 55 women in the sample. That's more than 10. And since there was 100 students total, that means 45 of them had to be not female. And that's also bigger than 10. Here, yes. There's 55 women, bigger than 10, and 45 not women, also bigger than 10. That's how the success-failure criterion works. So that's really easy for you guys to do. You just need to make sure that there's 10 that are in the category. We've got 10 women at least. And we also need 10 that aren't in the category. That's satisfied here too. Okay, well, now that we know that we're justified in using the central limit theorem, let's get all of our information out. There's not too much in here. For p hat, we can see that that's 55 out of 100. In other words, 0.55. Nice, easy math. For the sample size n, That's 100. And there's only one more piece of information we need. We still need the z-score. We need z. In other words, what are the cutoffs for the middle 95% of normal? And the reason I'm doing 95 is specifically because this problem told me 95%. What are the cutoffs for the middle 95% of the normal distribution? That's the z-score we're looking for, and that's why this is a backwards problem. Well, let's look at the table. Let's look at the table. 95%, this is one we've done a bunch of times in this class because it's really common, but I want to show you in the textbook again, just in case it's been a while and you feel a little rusty. Here's what we're going to do. I just opened up the textbook. You guys can do the same thing. And table of contents, let's see. At the end, we've got the distribution tables. Click on that. Here is the z table. This is the one that we need. If there's, oh, let me write one more thing. If 95% in the middle, then 2.5% for each tail. Right? 95 in the middle, got to be 2.5 left over for the stuff on the outside. If that doesn't make sense, you should definitely be asking me about that in office hours. So let's look for 0.025. Looking for 0.025, this is one that happens to be in the table exactly. You can see me highlighting it there. And that gives me my z-score, negative 1.96. We're going to use both of them. So we really think about it just in terms of the positive version. We're going to do both negative 1.96 and positive 1.96. So we say here, our critical z-score is 1.96. These z-scores that we're looking for whenever we're making a confidence interval, note, z-score for CI is called critical value. This thing, this 1.96, that's the critical value for this one. It's critical because it tells us how wide our confidence interval is going to be. But now that we've got that, z equals 1.96, we're ready to go. Let's plug everything into the formula. Our formula here, formula for this stuff, you can scroll up above to see it in our notes. I'm just going to type it out here. P hat plus or minus z times square root of p1 minus p hat 1 minus p hat all over n. There's the formula. Every single time you're going to do a confidence interval for p, and you're going to do it a bunch, that's what you do every single time. And we know what all this stuff is. We know p hat, we know z, we know n, so let's stick it in. I'm going to do the lower bound first, that's the negative one. First, lower bound. And here, p hat is 0.55. Since it's the lower bound, I'm doing the minus because we want to go down below. The z-score that we were thinking about here is 1.96. That's the critical value that we just found. And now square root 0.55 times 1 minus 0.55 divided by 100. That's the lower bound. Population proportion is probably bigger than that. Okay. Let's do the upper bound. It's going to be exactly the same thing, except this time I'm going to use a plus. So I'm just going to copy paste my work, and the only difference here is that I'm using a plus because we're going up. When I run this stuff, let's see, about 64%. So, in other words, here's our conclusion. We're done with the math. Here's the conclusion for this stuff. We are 95% confident that the true proportion of Denison students who are female is between 45.2% and 64.6%. I'm just going to round those off a little bit. The end. We just made a confidence interval. Yay! We started with only information about the sample, but now we're saying something about the entire population. I know there's no reason to expect that the whole population is going to be exactly equal to our sample result. 55%. That's just random chance. But we can say that we're 95% confident 95% of the time we take a sample like this. The true proportion is going to be between those ranges. Here's what we're saying. We think that the proportion for all Denison students is somewhere in that range, somewhere between 45% and 64%. The end. That's what confidence intervals do. Confidence intervals are all about estimating a population proportion. We think it's somewhere in this range. You might look at this and think it's not necessarily very good. 45% to 65%, that's kind of a big range. In the future, we'll talk about how to make that margin of error smaller. In other words, there are things we can do to make our confidence interval get narrower and to get a better idea of what's going on with the population. Okay, let's do another example. Here's example 2. This one is very similar, and if you followed example 1, you're already ready to do this one. Maybe it would be a good time to pause and try this thing out for yourself. It's going to be basically just the same as the previous one. Try it out, see if you can get the correct answer, and then come back and check in with me. I'm going to do it now. This one says, suppose we take a random sample of 60 Denison students and we find that 16 of them watch the Netflix show Love is Blind. Based on this, we want to estimate the proportion of all Denison students who watch the show, this time with 90% confidence. Let's figure out, with 90% confidence, how many Denisons, or what proportion of Denison students are watching Love is Blind. Before we get busy with the math, I just want to point out, think about what we're doing here. We've got information about a sample, and we're trying to say something smart about the population. That's statistical inference. We're making conclusions about the population here. Specifically, we're making an estimate, and that's what confidence intervals are all about. Let's collect our information. For our info here, I can see n is big enough. Since there are more than 10 in more than 10 successes and more than 10 failures. So we've got a sufficiently large sample size. NP is bigger than 10, and n times 1 minus p is bigger than 10. For p hat on this one, my p hat is, well, 16 students watched the show, and we had 60 total, so I'm going to leave it there. That's the sample proportion of students who've watched Love is Blind on Netflix. Okay, what about our critical value? We need the cutoffs for the middle 90% of normal. It's a backwards problem. So we need to figure out what are the cutoffs for the middle 90%. Imagine my head is the normal curve. If there's 90% in the middle, that means each of the two tails has to have 5%. Each tail has 5%. 5%, 90%, 5%, that's everything. So let's find 0.005 in the table. I'm going to switch over and take a look. I'm looking at the thing that's as close as possible to 0.005, and this is one where two of them are equally good. 0.0495 and 0.0505. Both of these are equally good. So we need to split the difference here. One of them is negative 1.64. The other one is negative 1.65. We'll split the difference. Use z equals 1.645. Split the difference. Those two are equally good, so I'm just using the one that's in the middle. Okay, cool. We've got all the information we need. Remember, our formula is p hat plus or minus z times the square root of blah blah. So let's do it. Here for the low bound, that's 16 out of 60. There's my p hat. Minus 1.645. That's the z-score that we just found. Times the square root of 16 out of 60 times 1 minus 16 out of 60 divided by the sample size, which is 60. Get a lower bound of 17-something%. If you want to, you could ask your calculator what 16 out of 60 is, but I wouldn't do it. It's going to be a really long decimal number, and that's actually harder to type in than just 16 out of 60. Also, if you round it too much, then you might not get a very good answer. So I really recommend doing it this way. For the upper bound, it's going to be exactly the same thing, except we're going to do plus. So I'm copy pasting, I'm putting a plus in right here. And when I run this stuff, I get 36%. So what have we concluded? Based upon this sample result, we are 90% confident that the true proportion of DU students who watch Love is Blind is between 17.3% and 36.1%. Based on this sample result, we're 90% confident that the true population proportion is between 17.3% of students and 36.1% of students. We have made an estimate for the population proportion based upon the sample result. That's a confidence interval. If you didn't get these on your own, I strongly recommend trying it again. Make sure you don't just watch me do it and go, that makes sense. Cover up the solution. Try to work everything on your own from start to finish and see if you can get the final answer. If so, you're good to go. If not, you need to figure out where your mistake is. Make sure you're coming to talk to me in office hours on Google Hangouts. That's where I'm doing my office hours. You're missing out if you're not going there. Don't try to do this stuff alone, and don't just let it go if you don't understand, because then you're going to miss that question on the quiz. Come get help. I'm going to hang out, I'm there 10 to 12, Monday, Wednesday, Friday. I'm also there at other times, and you can try to schedule appointments with me too. We can work something out. I know that we're not in person anymore, but I still want to be there to give you guys help. So help me help you. Let me know. Come ask me questions. Come get help. I can make up lots of examples. And speaking of examples, take a look at the description of the video underneath this thing on the YouTube page. You might need to click show more to see all the information, but look at the practice problem. Take a look at the practice problem for this video. I'm going to post the answer just like usual. If you can do that, you're good to go. Otherwise, come back and get some more practice and get help from me in office hours. And that's it for today. We'll do some more with, there's a lot more with confidence intervals, but this is the basic idea. See you next time.